discuss the ideal gas law. As a quick review, last class we went over the variables of pressure, volume, and temperature, remembering to keep your temperature in Kelvin. Also reminded you about the mole, and in this unit, our moles will represent the quantity of gas. We won't talk about grams of gas, we'll talk about moles of gas. And the gas laws that we did last time, I just want to point out, they're called the named gas laws. And those named gas laws are all about before and after. For example, with Boyle's law, we learned that pressure times volume equals pressure 2 times volume 2. So this was all about before and after, a before and after situation. P1 V1 equals P2 V2. So if this is the pressure, this is the volume. So what if I change the pressure? What will the volume be? So it's a before and after. Charles' law, another named gas law, was V over T equals V over T. So again, and it's V2 over T2. Again, this is the volume at this temperature. What will the volume be at this temperature? So it's all about before and after. Today, we're going to cover not a before and after gas law, but we're going to cover what are the conditions right now, and that is best described with what's called the ideal gas law. PV equals nRT, PIV-NERT, where we're using pressure, volume, temperature, and moles. So the same variables that we went over last time. But now there's this R, and what on earth is that R? Well, that R is the ideal gas constant. And if we were to rearrange this equation just algebraically, if we want to rearrange PV equals nRT to solve for R, we would divide this side by N and T. And whatever we do on that side, we have to divide this side by N and T. And this N will cancel out this N because it's over each other, and this T will cancel out this T. So PV over NT, or pressure and volume over moles and temperature, will give us R, which is the ideal gas constant, R. And if we move to the next slide, are there any variables that we can put in that's going to make this work for us? So we know something from class, from the mole map, way back when, remember that mole map, that 1 mole of any gas, so 1 mole of gas, occupies 22.4 liters at STP. And last class, you were reminded that STP is just the temperature and pressure, standard temperature and pressure, so it's 2 variables. The pressure is 1 atmosphere, and the temperature is Kelvin. So this is the pressure, and Kelvin is the temperature, and liters is volume, and this is mole. So we have our N, V, our P, and our T. So if we plug it in here, if we literally plug in pressure, so 1 atm, and we multiply it by our 22.4 liters, and then we divide that by 1 mole, which is our N, and our temperature in Kelvin is 273 Kelvin. What's important here are these units, and we can literally do this in our calculator. And when we do that in our calculator, we will find that we get 0.0821, and the units are liters, atmospheres over mole and Kelvin. Liters and atmosphere over moles and Kelvin. So that is R. But what does that mean specifically is that this is how these units relate to each other. It is a constant, and it is this specific constant if you're using these units. If you were to change the units, you would have a different R value. So and there are other R values depending on the units. There's an R value for kilopascals, but we're using ATM. There's an R value for milliliters, but we're using liters. There's an R value for Celsius, but we're using Kelvin. So there are different R values, but we're going to stay consistent, and we're going to use the R value of 0.0821, and that means for the problems that you do in this class, your volume must be in liters, your pressure must be in atmosphere, and your temperature must be in Kelvin. So a lot of these problems are going to be multiple conversions before you just plug and chug. And when I mean plug and chug, you're just plugging in the appropriate value for each variable. Give it a try. So for this one, it says what pressure is required to contain 0.023 moles of nitrogen gas in a 4.2 liter container at a temperature of 20 degrees Celsius. So hopefully something is sticking out to you right now. Hopefully the 20 degrees Celsius is looking a little odd. We need to convert this to Kelvin. So we will add 273 to get 293 Kelvin. So 293 Kelvin. So that's our T. We're given a volume, we're given a T, and we're given an N. So we're going to use PV equals nRT, PivNert, nRT. We know our R, and we've matched our units Kelvin, liter, and mole to be able to use that R value, and we're solving for pressure. To solve for pressure, we need to divide this side by V, and whatever we do on one side of the equal sign, we have to do it on the other side of the equal sign. This V will cancel that V, so we'll get pressure equals nRT over V. Now we're plugging and chugging. So here is the plug and chug. We put in moles, our N, here, 0.023. R is the 0.0821. 293 is our temperature, and we divide it by the volume of 4.2 liters. Now, an important thing to look at is the units, how the units cancel. This mole, whoa, let's undo that. This mole here cancels, it's on the denominator, it cancels with a numerator mole. This denominator liter cancels with a numerator liter. This denominator Kelvin cancels with a numerator Kelvin, and that leaves us atmosphere. So when we figure this all out, our units are going to be atmosphere, which is good because that is a unit of pressure, and the question is asking us for pressure. Here is one. What volume will 2 moles, that is our N, of nitrogen occupy at 720 torr, that is our P, and 293 Kelvin, that is our T. We automatically know R as long as we keep our units, and our R is 0.0821. And it's asking asking for volume. So volume equals nRT over P. And how would I get that? Well, it's normally PV equals nRT. I divide both sides by P. Now, in order to use this R, I need to put this 720 torr into atmospheres. To do that, I'm going to divide by 760 because 1 atmosphere is 760 torr. So if I divide it by 760 torr, and 1 atmosphere is 760 torr, then my torrs will cancel out and I'm left with atmosphere. So I can put my 2 moles right in there for N. I'm going to use 0.0821 for my R value. My temperature value is 293, that's in Kelvin, and I'm going to divide by my pressure, which is 0.95 atm, atmosphere. So I have my atmosphere, I have my Kelvin, I have my moles, so if I can use this constant, not a problem. And then I will get my volume, and the constant tells me what my volume units are going to be, liter. So when I do the math on here, I will get my answer. So in my calculator, 2 times 0.0821 times 293, it equals, divided by 0.95, it equals, and I get 51 liters. Not bad, 51 liters at that point in time. That's the volume of this many moles of nitrogen gas, this pressure, and this temperature. That's the volume it will take up. Now, this next question shows us 25 grams of carbon dioxide, and it's asking what's the pressure will be exerted by 25 grams of CO2 at a temperature of 25 degrees Celsius and a volume of 0.5 liters. Well, only the V is in the units we need. The 25 degrees we have to add 273 to. So we will get 298 Kelvin, 98 Kelvin. And the 25 grams of CO2 we have to divide by the molar mass of CO2, which is 44.01 grams per mole. And that means our grams will cancel out and we'll be left with mole. And if we're solving for pressure, that means nRT over V. I've divided this side by V. I have to divide this side by V. So P equals nRT over V. And my answer will be in 1 sig fig. So take a moment now, see if you can get the answer, and I hope this helps.